Okay, how we doing? It's time for some year 13 stuff, ladies and gentlemen. And yesterday we were looking at the rate equation and the Arrhenius equation. So essentially I gave you kind of a best of, if you like, in terms of my hints and tips as to how to deal with the rate equation, what it all means, what the Arrhenius equation means, and basically how to rearrange it and make light of the questions that we come across on the Arrhenius equation. Because so many students say to me all the time, "Oh, I hate that, it's a nightmare." It really, really doesn't have to be. If you've got an understanding of how it works and how to rearrange it, then actually it's a bit of a walk in the park. Okay, so who have we got in here? We got Jezin, we got Sanan, Ruhab, hello, Cecilia, hello. How are we doing, guys? Make sure you say hello in the chat. Make sure I know that you are here. Hey Benyon, how are we doing? Anush, how are we doing? So we are going to be looking at and your usual boy Ruhab. Yeah, hello. Hey William, Abab, Jenny, hello. So hi Miss C, back again for more. So yeah, I think we're going to basically have a go at some questions today, if that's okay with you guys. But take the knowledge we picked up yesterday in the last session and apply it to some common exam questions. So these are questions I used in my live class on this. So my regular live class that I do for TT subscribers. We covered this way back, I think in like October, something like that. So like I said, those sessions, if you click on the content guide from within the Exambulance in that first section, any of the buttons at the top for your exam board, you'll see a padlock there. I've unlocked the lessons I've done on rates and the Arrhenius equation, and I've got unlocked within the course as well some of those tutorials that we've got within our content guide. Okay, so are we ready? Do we feel like we want to do some questions? I'm going to share the screen. Let's go for this. Okay, so iPhone, iPad, there we go. Boom. So hopefully you guys can see this nice and clearly. I am going to, let's move these windows around a little bit. Okay, so can we read that okay on the YouTube screen? Just give me a yes if we can. Give me a no if we can't, obviously. Let's take a sip while you answer that. Sweet. So first point, in our exam guide, we've curated loads of papers for you. So what we've done is we've basically taken all the OCR and EdXL papers and basically blanked out any questions or parts of questions that you guys don't need to know for AQA, all right? And we've done the same for all of them, okay? So if you're EdXL, we've curated AQA and OCR. If you're OCR, we've curated AQA and EdXL. So you've got access to loads and loads of questions in there, okay? Nothing at all, Edith, we're just getting started. So essentially, rates is one of those things where, okay, there are little nuances that you need to know that are slightly different. Like some of you need to know about half-life, some of you need to know about rate determining steps, so on and so forth, okay? But essentially, the rate equation is there for everybody. So, we've given you access to all those other questions as well, and you don't need to worry about whether it's relevant to you or not, because any questions are irrelevant, we've blanked out for you, all right? So, the initial rate of reaction between gases D and E was measured in a series of experiments at a constant temperature. The results are shown in a table below. So this is something like we looked at yesterday, guys, okay? Rate determining step for AQA, I think it is. Yeah, but there's a question we're going to be looking at, Amy, so we will look at the rate determining step. So we've got these 3 experiments here, D and E concentrations, initial concentrations, and of course, the initial rate. So deduce the order of reaction with respect to D and with respect to E. So let's zoom in on this a little bit more so we can see them. So let's do, which one should we do first? Let's do E. Yeah, let's do E because these are the same. Okay, so what we can do is actually find E really, really easily by looking at the difference between these two. So what I'm going to do to find the difference between those two is, so E, so I'm going to do 1.75 divided by 8.73 times 10 to the minus 1. That's what we're going to do there. I'm going to find the difference, the factor increase on there. So 1.75 divided by 8.73 times 10 to the minus 1. And that's basically 2. Okay, 2.044. Okay, so basically times 2 for those two. What's happened to rate? Well, that's 1.57 times 10 to the minus 1 divided by 3.92 times 10 to the minus 2. So we know for a fact it's had an impact, but how much? And that is 4. Okay, so rate has increased by a factor of 4. So therefore, concentration of E equals what, guys? What's the order here with respect to E? Good, second order. Okay, so it's second order with respect to E. So I'll put that down there. Okay, now we know it's second order with respect to E. We can go ahead and find D. All right, so I'm going to change the color so we know what we're talking about. So for D, which two are we going to choose? Well, we have got a choice, of course, haven't we? Okay, so we've got 1 and 2. Or we've got 1 and 3. Okay, so we can use whichever one we want. So let's find out the difference between these two. So that is 1.88 times 10 to the minus 2 divided by 1.25 times 10 to the minus 2. So what's that? Well, somebody already said it's second. Okay, so that is times 1.5. Which is weird, all right? But let's go with this. So which ones are we going to choose? Let's choose 1 and 3, okay? Let's choose 1 and 3. So we know that E is second order, okay? And we know what factor is E increased by. So that is 1.75 divided by 5.81 times 10 to the minus 1. And that's 3. That's a 3-fold increase there. Okay, so let's take that into account first. All right. So if E has increased by a factor of 3, that should cause a 3 squared increase in the rate. Okay, so it should cause a 3 squared increase in the rate. So that's 1.16 times 10 to the minus 2. So what's 3 squared? So that's 9. Times a 9-fold increase gives us 0.1044. Okay, 0.1044. All right, so that's the increase in rate that E will have caused in the initial rate. Okay, in the initial rate. So now we need to find the difference between these two. We've accounted for the change that E has caused. Now we can find the now we've accounted for that. We can find out what the change in rate is for D, okay, what D has caused. So which is the bigger number there? So it's 1. Okay, so that's 1.57 times 10 to the minus 1 divided by 0.1044. That is 1.5. Okay, so there to there is times 1.5, which is the same as the increase in concentration for D. So therefore, D is first order. Okay, so that is our final answer. Okay, so that's why. So you can see what we do there. There's always an in somewhere. There's always one in there where the concentration of it's changed and all the others remain the same, which is in this case E. Now to find D, okay, all we need to do is account for the effect that E has had. Now we know what order it is. And then look at the difference after we've calculated the effect on the rate that E has had. Look at the difference between that number and the number we actually have got for that rate, and then that tells us the effect that the concentration of the change in concentration that D has had. Okay, so it's really hard to put into words, this, isn't it? Okay, so the steps are, all right, find the order with respect to the one where that's the only one that's changed. Okay. We can try that, Ibrahim. Absolutely. Okay. Well, we'll try another one in a second. Okay. So then to find the other one, D in this case, you account for the change in E. and then find what the rate should be, okay, in terms of the change in E. So we've accounted for the increase in concentration of E, and then we look at the difference, okay, between these two numbers, the delta between these two numbers, the one we calculated after taking into account E and the one we've got. And that is 1 times 1.5, which is same as the change in concentration of D, hence it's first order. Yeah, times 9, okay? So what I did was I took this number, times it by 9, because this has gone up by 3. We know it's second order, so basically we're timesing it by 3 squared, which is 9, to get that number, and then we do that. Okay, there is a document with all these questions on and the mark schemes in the live classes that I've unlocked for you guys within the course. So you can access these questions and the mark scheme and me going through it in the live class that we did at the time. Okay, that's it. Okay, times 9. That's it, Rasep. So on to the next part of this question. Suggest why the initial rates of reaction are used to determine these order rather than rates of reaction at other times during the experiment. So I'm going to give you guys a chance to write your answer in here. So suggest why initial rates of reaction are used to determine these orders rather than rates of reaction at other times. So why are we using initial rate and not any other rate that can be measured at any other point during this reaction? Highest conc of reactants at the start because reactants are used up. Yes, reactants are used up as time goes on. Essentially, yeah. I mean, you've actually absolutely got it. Okay, yeah, reactants are used up and the rate changes. The answer's not wrong. It's definitely first and second order for those two. Yeah, so reactants are used up. So essentially, the initial concentrations are known, okay? As the reaction proceeds, all right, as the reaction proceeds, then essentially the reactants get used up, and therefore we don't know what their concentrations are. It's like a kind of stab in the dark, isn't it? So we have to use the initial concentrations for these equations, okay? So concentrations are known, initial concentrations are known only, okay? So at any other point, then the reaction concentrations are not known, okay? So what we can say is that the concentration of reactants decreases over time, okay? And that would get you the mark for that one there, okay? Yeah, it's tough, isn't it, Edith? Okay, so you have to read it twice almost. I had to read it twice when I did it. Suggest why initial rates of reaction are used to determine this order, rather than rates at other times during the experiment. Okay, so yeah, that's it. That's it. So, secondly, part B, well, it should be part C, shouldn't it really? State how the initial rate is obtained from a graph of the concentration of the product against time. So I'll talk to you again at the end where this PDF is, guys, but just let's focus on answering these questions together for now, okay? So state how the initial rate is obtained from a graph of the concentration of product against time. Boom, that's it. Absolutely, that's all we need to do. So we need to draw a gradient from time 0, okay? Calculate gradient, and then that equals the rate of reaction. Okay, so that's all we have to do. Yeah, that's all it is. So what we'll get is graph of concentration of the product against time. So, you know, it's kind of like, oops, like that typical gradient. And then what we do is we just draw a tangent here, like so, and that calculate the gradient. And that is, because it's concentration against time, the rate will be moles per decimeter cubed, concentration against time, seconds. So moles per decimeter cubed per second, moles per decimeter cubed per second. So that's all we have to do. That's like year 1 stuff, isn't it? Drawing a tangent like that of rates against, of finding the rate of reaction, initial rate of reaction. That's all it is, okay? So on to the next one. Which one are we going to go on to? Which one did I decide we were going to do? Let's have a look at this one, okay? Oops. Okay, so a student carried out an investigation into the rate of reaction between propanone and iodine in acidic solution. There's a multi-step reaction, but the overall equation for the reaction is this. Okay, so we know it's multi-step. They've told us this. All right. We've got the overall equation. In the first part of the investigation, they measured how the concentration of propanone changed over time, and results as shown in the graph below. So this propanone, of course, being a reactant, we do get a decrease in the reactant over time. So as we said before, we've got the highest concentration at the start, lowest concentration at the end. We can see how it's being used up. Okay, so it's used up really, really quickly to start with, and then it slows down. Okay, it's the opposite of that, isn't it? As the products get produced, that slows down over time as well. Okay, and that obviously always comes back to year one. Oh, well, concentration is decreasing, therefore fewer successful collisions, or a lower frequency of collisions, and so on and so forth. Okay, so over the page, explain how the graph shows that a reaction is first order with respect to propanone. Use values from the graph to justify your answer. So how do we do this? And I think Jezin, apologies for the pronunciation. You're absolutely right. It's about looking at half-life. Yeah, absolutely. Yeah. So the graph is a constant half-life. Absolutely. Okay. So what we can do is we can find the gradient at two different points. So let's say I found the gradient here, okay, at 64 times 10 to the minus 3 moles per decimeter cubed. And what's a logical number to use to find a second rate of reaction? What do we think? Where would we draw our second tangent? Yeah, 32. Absolutely. Okay, so 32 here times 10 to the minus 3, because obviously, you know, that's what it says there. So we just draw another tangent here as well, wherever that might be. Like that's a bit rubbish. And we find the gradient of those two tangents. Okay, and therefore we find the rate at one concentration and the rate of another. Why 32? Because it basically it's halved, hasn't it? Okay, we've given ourselves nice numbers to work with. That's it. Okay. So here's one I prepared earlier, kind of thing. So the half-life, I'll tell you what. So at 64 times 10 to the minus 3, the rate equals 0.05. And at 32 times 10 to the minus 3, the rate equals 0.025. I've done the calculations for you, okay? So that's all we need to do is find the gradients, and then that tells us the rate, okay? So we've got a concentration and a rate. So what's happened to our concentration here? Well, concentration has been halved, okay? Rate has been halved. Therefore, order with respect to propanone equals first order, okay? First order. Okay, so everyone happy with that? So we can just take, when you've got these concentration against time graphs, you can find the order of reaction really easily by just taking two tangents. It's like working out half-life. Not everyone needs to know half-life, but everyone needs to know how to do this. And basically just looking at the difference. You're basically creating the data that we've been given in like a table like this one, yeah? So that's what you're doing here. So next up, in the second part of the investigation, the student investigated how different initial concentrations of iodine and acid affected the rate of reaction. The following results were obtained. So orders of reaction with respect to I2 and H+. So I'm going to give you guys a few minutes, maybe 2 or 3 minutes. I'm going to be quiet. I'm literally not going to say anything. I'm going to get you guys to work that out. Okay. I'm going to get you guys to work that out. So I'd like the order with respect to iodine and the order with respect to hydrogen ions, please. I'm going to give you 2 minutes. Yeah. Okay, brilliant. Absolutely. So for iodine, I would pick out these two. And for H plus, I'd pick out these two. Okay, so yeah, it is a lot easier than the last one we had, right? Because, you know, we've got a fair test. We're only changing one variable for each of them, aren't we? So, you know, you can show your working there if you need to, but essentially, as you say, iodine is 0 order and H plus is first order. That's it. Okay, so 0 order and first order. Cracking. So write the rate equation for the reaction. Now, we need to be very careful here. All right, I want you to write the rate. Whoa, jazz straight in there. Okay, I'll tell you what, I'll start us off. Rate equals K. Yeah, how do we describe how we know? Well, looking at that table, I've picked experiments 2 and 3, if you like, for iodine. Iodine's gone down. Iodine concentration has been halved. Okay, the initial rate hasn't changed at all. That's why it's 0 order, has no effect. H plus is first order. I've picked 1 and 3. H plus concentration has doubled and the initial rate has also doubled. Iodine remains the same. So that's why, Edith. KH plus, not quite. Okay. Jazz and George, you have got it. It is K, CH3, CO, CH3, 2, H plus, and that is your rate equation. Okay, that is your rate equation. That's it. Either way around, doesn't matter whether it's the H plus or the propanone first, but both of those are in there. Why some of you wrote H plus, completely understandable. What we mustn't forget is that in a previous question, we already stated that it's first order with respect to propanone. Okay, so Raseb is from the previous question. Yeah. So this is just, I don't know, typically what the exams, the way in which the examiners can actually fox us, shall we say? It's kind of like, oh, I forgot about propanone, especially in an exam situation. You're like, oh my God, like, yeah, that's it. Yeah, yeah, it's a whoopsie, but that's fine. Okay. As long as you make your whoopsies here and not in the exam room. Well, that sounds a little wrong, doesn't it? Yeah. Don't do whoopsies in the exam room. I think that's a mantra if there ever was one. Yeah, it is about attention to detail. Absolutely. So next up, calculate a value for the rate constant in the rate equation and using the rate equation and state its units. Okay, so how do we do this? Well, we just pick a line. Okay, we've got the concentration of propanone. All we have to do is just pick some numbers. So for example, we just pick this one here. And all we need to do is just put the numbers in. So the rate here is 2.1 times 10 to the minus 9 equals K times 1.5 times 10 to the minus 3, which is our concentration of propanone, times 0.02, which is our concentration of hydrogen ions. So therefore, K equals 2.1 times 10 to the minus 9 over 1.5 times 10 to the minus 3 times 0.02. And that gives us, let's have a look at your rearrangements here. Not quite. It's rate over everything else. Rate over everything else. Okay. So our answer here, has anybody got an answer for me? I've got an answer. Yeah, good. So that is 7 times 10 to the minus 5. Our units, ladies and gentlemen. Now, I'm pretty sure only AQA need to figure out units, but here we go. Moles per decimeter cubed per second all over moles per decimeter cubed for this one times moles per decimeter cubed for this one. Now, all we need to do is cancel out as many moles per decimeter cubes as we can. Okay. OCR2 as well. Okay, fair enough. I'll take that one on the chin. It's hard to hold all that information in my head. So we end up with, if we go down here, per second over moles per decimeter cubed. So to bring that at the top, we just invert our units. So we end up with moles minus 1, decimeter 3, S minus 1. Or you can write it as decimeter 3, moles minus 1, S minus 1. Officially, that's the proper way you should write it. But you know what? The exam boards, they really just don't care. Okay. Oh, cool. SM for OCRB salters as well. Thank you very much. I've learned something there. Okay. So this is a typical type of thing they can do to you. They give you a practical. All right. And they give you data and you have to use this data. There's no way they can ask you any questions on rates other than giving you data. Okay. So you've got to be prepared for that. Now, rate determining step, ladies and gentlemen. I'm going to give you a rundown, okay, of what the rate determining step is. So a very quick lesson on the rate determining step, because I know not everybody has to do this, okay? So let's take our rate equation here. So rate equals K, CH3, CO, CH3, H plus. Now, what does this tell us about the rate determining step? What does the rate determining step? It's like a mechanism, so it's a multi-step process. What does that tell us about the rate determining step? It's the slowest. That is a fact about all rate determining steps, yes. Oh, good. Team, they are in the rate determining step. So here, okay, both of these reactants are in the rate determining step. So they might say suggest a rate determining step. So I would go CH3, CO, CH3 plus H plus, and maybe that gives us CH3, COH, CH3 plus, okay? And then that goes on and does something else, but this would be the rate determining step. Not only do the reactants in the rate equation tell you what is in the rate determining step, but they also tell you how many, okay? So let's say you had a rate equation that was basically, I don't know. So I'll tell you what, this one, let's do this one, okay? So K, NO2, 2, okay? So rate equals K, NO2, 2. So the order of reaction tells you not only that, you know, sorry, the reactants in the rate equation not only tell you what reactants are in the rate determining step, but how many as well, okay? Rate, how many as well. So here, if it's second order, 0 order equals 0 in the RDS. First order means there's one of them in the rate determining step. Second order means there's 2 of them in the rate determining step. So when something's second order, that means that you have 2 NO2 molecules in the rate determining step. Now, what they actually produce, I don't know. Maybe it's NO and NO3. Who knows? Okay. Or maybe it could produce N2O4. Who knows? Okay. The thing is, those questions are always phrased like suggest the equation for, you know, the rate determining step. You're not expected to know exactly what happens unless they give you more clues, but suggest the rate determining step. Okay. Yeah, that's it. So 2 moles of it are present in the rate determining step. Okay. So if it's 0 order, it's not in the rate equation, so you don't need to worry about it. If it's first order in the rate equation, then there's 1 molecule of it in the rate determining step. If it's second order in the rate equation, you know there are 2 molecules of it involved in the rate determining step. Okay. SM aviation, you can think of the rate determining step as a slowest reaction. For analogy, you can use baking a cake. Bake a cake requires you to cook it for a long time. So the rate determining step would be the cooking. Yeah, absolutely. Another analogy for the rate determining step is that if you're in a relay team, okay, you're only as fast as your slowest member. All right. So if you've got to get, let's say you're in a race and you've got to get everybody across the line to win that race, all 4 of you, then you're only as fast as your slowest member. And that's what the rate determining step is. Okay. You could put 2 NO2. I'm pretty sure you get away with that. Okay. Yeah. So what about when a question asks you to write down a multi-step process? That is a very good question. Well, let's have a look at this one. So explain what is meant by the rate determining step. Now, basically what I'd write here is, so we've got a question. Let's read the question first. That would help, wouldn't it? So another multi-step reaction is the one between nitrogen dioxide and carbon monoxide. The overall equation is that. We got the rate equation. The first step is the rate determining step. Explain what is meant by the rate determining step. Well, it is the slowest step in the reaction. Okay, slowest step. Oh, Ibrahim, where did you get that from, SM? Terrible, terrible. I thought it was a little flawed, to be honest with you. Anyway, species that appear in the steps up to and include the rate determining step are in the rate equation. Okay, so how do you know that carbon monoxide is not involved in the rate determining step? Well, how do we know that carbon monoxide is not involved in the rate determining step? Yeah, good. It's not in the rate equation. Absolutely. Okay, absolutely it's not in the rate equation. Now, write equations to show a possible two-step mechanism for this reaction. Right. Well, we need to look at the overall. So I would say we can't do, can we? We cannot do NO2 plus CO. Why can't we do NO2 plus CO? Yes, CO is not in the rate determining step, is it? So our rate determining step must be this NO2 plus NO2. How do we know there's two of them in there? Even though there's not two here, it doesn't matter. It really doesn't matter, okay? So NO2 plus NO2, let's say that goes to N2O4, just for giggles, okay? Because we don't know what two lots of NO2 come to, okay? So N2O4 is what we get here. So what might be the second step then, ladies and gentlemen? Bearing in mind, we need to make these products. Yeah, good. Then we can have N2O4 plus CO. Now we need to include this somewhere. So what could that actually give us? Well, at some point, we have to make the product of the overall equation. Okay, we have to make the products of the overall equation. Otherwise, well, we're not doing what the equation wants us to do, are we? Okay, so what do you think our products are here, ladies and gentlemen? Good, yes, in NO and CO2. But the thing is, we've got to balance this now, haven't we? Okay, so we've got to have two lots of NO. And I should imagine, I think that's it, isn't it? Two lots of NO, yeah, and two lots of CO and CO2. It's 2CO, 2CO, and 2CO2. Okay. So that would be my suggestion for a possible two-step mechanism for this reaction. Okay, now it's balanced. Now, a little hint for you, a little bit of magic. Let's do down here, NO2 plus CO goes to NO and CO2. Okay, that's the overall equation. Now, let's cross out, eliminate everything that is not in our overall equation. Well, N2O4 didn't go in there. And that can disappear as well. So essentially, if we combine these two now, if we take our two steps, get rid of these, N2O4 is like an intermediate, isn't it? It doesn't appear in our actual equation. It's like, oh, it's there 1 minute and gone the next. It's produced and then used up. So it's like an intermediate. So we can cross that out. And then what we can do is merge those two equations. So we end up with 2NO2 plus 2CO gives us 2NO and 2CO2. Well, that's the same as that one. It's just doubled up, right? So what happens is when you cancel out, when you get rid of any intermediates you make, then you merge those two equations, you should end up with the overall equation. So that's like a great kind of common sense check at the end of it. Okay, great common sense check at the end of it. Okay, so that's just a little hint there that you can use in order to write those two-step reactions. Okay. Good, Rasa. Thank you very much. I'm glad you approve. Right, I tell you what, before we run out of time, let's do 10, 15 minutes on Arrhenius. Yeah, so, well, basically, what I would say is this is our answer. Okay, that would be what gets you the 2 marks. You don't need to cancel down, but if you want to double check that you have actually fulfilled the brief, if you have actually, done 2 steps that would give you the overall equation, that's your double check. Okay, that's all it is. Okay. Yeah, it would, absolutely. Okay, so if they asked you to come up with a 2-step mechanism, then you can use that technique at the end there of cancelling out the intermediates and merging the 2. That will tell you your overall equation. Okay. You needed to balance it, Ruhab. Yeah, you really needed to balance it. Okay, so hopefully that really helps, guys. Okay. Now let's do some Arrhenius. Who's up for some Arrhenius? Will he always give you the rate for the 2-step mechanism? Yeah, I mean, the questions tend to be bundled in together in terms of what's the rate determining step. And, they may ask you to identify it, maybe from a list of equations. They may ask you to write the equations. It really, they mix it up a lot, don't they? Okay, so which one are we going to do? Let's do not that one. Let's do this one. Okay, so if we can see that, okay, let me zoom in as much as I can. So a series of experiments is carried out with compounds C and D using data obtained. The reaction between compounds, because the equation for the reaction between the 2 compounds is deduced to be this. So rate equals K times C times D. In one experiment, the initial rate of reaction is that, 3.1. When the initial concentration of C is 0.48 and the initial concentration of D is 0.23. Calculate a value for the rate constant and give its temperature. So again, a classic rate question. Are we all okay with this? I don't need to get you to do this, do I? We've just done an example like this. Okay, sweet. So just so we're aware, the answer to that question is 0.0281, and the units are moles per decimeter cubed per second. Okay, so that's our answer there, 0.028. Oh, Miss C, you're like dynamite on this, like, all right, like grease lightning. Right, this is what we're really interested in. Okay, so I'm going to give you guys, this is 4 marks, this question. I've not made up the number of marks this is worth. This was actually worth 4 marks. So an equation that relates to the rate constant K and the activation energy EA and temperature is this. Recognize that, ladies and gentlemen? That is the natural log of the Arrhenius equation. Okay, so we've taken the log of everything in there. Use this equation and your answer from question 3.1, which was 0.028, and that's K. To calculate the value in kilojoules per mole for the activation energy of the reaction. So we want activation energy here, okay? Yeah, Arrhenius equation, it depends on your exam board. Sometimes it's in the data sheet. Sometimes they just put it in the question. It depends on the exam board. So 25 degrees Celsius, Ln A is 16.9, gas constant is 8.31. I would like you guys to calculate the answer, okay? Moles minus 1, decimeter 3. What did I say? Oh, yeah, so it's decimeter 3, moles minus 1. My bad. Thank you. Right. 4 marks. I'm going to give you 2 minutes to work out the answer to this. So what's the activation energy in kilojoules per mole? 2 minutes, starting from now. Ruhab, that is a very good question. The answer to that is yes. Select the next question. 50.7, 50.7. Really happy you haven't got a calculator. You can't do it in your head. Edith, Yasin, don't worry about it. Yeah, that's yeah, they're not the answers. Don't worry, don't worry, don't worry. Ibrahim, did you do it in your head? $15.82, 48.2. All right, bit of physics knowledge there from SM Aviation. 50.74, 50.7. So I think the general consensus here is absolutely 50.7. So how do we actually do this, ladies and gentlemen? So we need to rearrange this. Now, of course, what we want to do is make EA the subject. Okay, so the first thing I'm going to do is this. I'm going to do minus EA over RT equals ln K minus ln A. Okay, so ln K minus ln A. So obviously that's not good enough. We need to rearrange that further, don't we? Okay, so let's do minus EA equals ln K minus ln A times RT. Okay, so that's what we've got there. So put some numbers in. Let's do it in black now. So ln K is, what is ln K? Ln K is minus 3.572 minus ln A, which is 16.9, multiplied by 8.31, which is R, multiplied by 298, which is 25 degrees in Kelvin. It needs to be in Kelvin. So it's a lot like your ideal gas. Okay, your temperature needs to be in Kelvin. Okay, where did I get minus 3.572? Well, we've got K. So ln K is ln on your calculator, and then 0.0281. And that gives you minus 3.57. I know it's really small, but it's minus 3.57 there. Okay, whoops, like so. Okay, that's it. So once we put all that into the calculator, we end up with 50696 joules per mole. Joules per mole. So that's our answer. Okay, we get it in joules per mole. Why is it in joules? Because if we look at this, our gas constant, that's the one that's got joules in. Okay, so that's why our answer for activation energy comes out in joules per mole. Of course, to get that into kilojoules per mole, divide by 1,000, and to 3 significant figures, that comes out as 50.7 kilojoules per mole. So it's about the rearrangement of this. Okay, so yeah, another way of remembering it, EA equals RT ln A times ln A minus ln K. Okay, so it's just those rearrangements that I talked to you about yesterday. Okay. No. Okay. Good, Benyon. I'm pleased about that. Why do we have to make it minus? No. I mean, essentially, this is a negative number that comes out anyway, I think. So this comes out, yeah. So actually, this comes out as minus 50. Okay. So essentially, what it is minus EA equals minus 50. So therefore, EA equals 50. Does that make sense? Yeah, EA is always positive. Always, 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 always positive. Okay, that's it. How do we get 0.0281? Well, it was from the previous question. We calculated K from the previous question for that reaction. Okay, good, Miriam. That is why I'm here. That is why I'm here, to make things simple. Right, I tell you what, let's look at a graph question. because I think that's really important before we run out of time, and we are going to run out of time. So we've got a graph here, our ln k versus 1 over t. Okay, ln k versus 1 over t. So a student carries out an investigation to find the activation energy and the pre-exponential factor A of a reaction. So the student determines the rate constant K at different temperatures, and the student then plots a graph of ln K against 1 over T as shown below. So we've got a ln K versus 1 over T graph here, all right? So the first question is, draw a line of best fit and calculate the activation energy in joules per mole. Give your answer to 3 significant figures. So we need to draw a line of best fit. So what we do here is, as best I can, like so. Okay, so that'll be my line of best fit. So how do we do this then? How do we actually find the activation energy? What's the first thing we need to do? Good, Benyon, absolutely. So we find the gradient. Oop, I can't spell. Okay, so that is dy by dx. Now I can tell you the answer to that rather than us all kind of flounder around trying to calculate it from my screen. So that is, well, dy is, I did it at minus 31.5 times, minus 27.2 all over 5 times 10 to the minus 3, and that equals minus 860. That's our gradient, okay, is minus 860. What we do know is what, okay? So EA equals the gradient times what, guys? It's not over RT. It's not over RT. It's gradient times R, because the gradient equals minus EA over R, okay? Because the T has been brought out of this equation now, okay? Because it's like a y equals mx plus c graph, all right? So the grade EA equals gradient times R. So we could say that, okay? So minus EA equals minus 860 times 8.31, all right? So basically our answer is positive, because let's say they cancel out, positive 7146 joules per mole. Okay, that's it. Okay, just R. So then use the graph to calculate the value of the pre-exponential factor A. Where do we find A? We talked about this yesterday, ladies and gentlemen. When it says calculate, we need to do a little calculation, but how do we find A? Oh, where the 860, that's just the gradient that I calculated. Okay, sorry. Okay, so all I did was find the gradient of that graph, okay, which is minus 860 using the figures that we've got, okay. Boom, you guys are on it like a car bonnet. That is our y-intercept. So if we look at our y-intercept, that is, what's that, 31.35, just for giggles, okay? So that is ln A. So ln A equals 31.35. Therefore, A equals what? What do we need to do with that number? Good, E, okay? So it's shift ln, which is our E, and that's 31.35. And that gives us 4.12 times 10 to the 13, which is a pretty big number, to be fair, okay? How do we know it's E? Oh, like the little e that's on your calculator, because ln A, okay? So basically to get from ln A to A, we need to do e to the power of ln A, okay? E to the power ln A. That's what we need to do. So again, you know, if you want to have a go at some questions, if you want to, on the lives that I did, you know, these questions are there, okay? This actual PDF, and I go through this with the class. I go through every question with the class, and the mark scheme's there as well for you guys to use, okay? So, you know, you can fill your boots on these if you want. And as I said, those content guide lessons are also there for you guys to look at for the next 24 hours. Okay, so tell you what, let me just show you really quickly. If I go to courses, just bear with us a sec, guys, and I'll show you exactly how to get to these, and I'll show you inside the course because I know some of you are newbies. So if you've got, let's have a look. Bear with. Oh, damn it. It's not what I wanted. Okay, so let me just share my screen. Okay, so what you guys should be seeing now is inside the Exambulance. So all you need to do is pick whichever one. If you're in this top section, you got links to the content guides. So let's say OCR content guide. I'm going to open it in an incognito window, which I need to stop sharing and reshare, which is annoying. Share, which one do I need? This one. So what you find in here, okay, is these padlocks are the ones you can see. So in terms of the A live recordings, you just go down to either of these two, and in there you will find the recording of that live class that we do every week at TT for our subscribers, and links to the PDF and mark scheme. Okay, so you can see me here in my periodic table mug. All right, but equally, you'll see down here, this is stuff I was doing with year ones, so year 12s. And this is the section where I've unlocked a few videos in here to help you as well. Okay, so these are absolutely specific to your exam board. It'll look slightly different depending on what exam board you're in, because of course, you know, all these sections are bespoke to your exam board. Okay, so let me just get back to see what you guys are saying. Okay, no, you don't have to have a subscription to access those particular ones. Because I've unlocked them for you just for the next 24 hours. Okay. When we do something different tomorrow, then we will be, basically, I'll be unlocking a different part of the course for you so you can use those to complete your notes. Okay. Yeah. Ruhab, don't give up the day job. So, although I need to go over Arrhenius, I know a lot more than I did before. That's good. That's good. Absolutely. So, you know, if you want to access those content guide videos, you can for the next 24 hours only. And I will reconvene with you guys tomorrow. So again, yeah, it's only available until basically lunchtime tomorrow. All right. So I'll give you 24 hours to access that. Well, it's been open since actually yesterday because we're still talking the same topic, aren't we? Okay. So just before the live class, I'm going to swap out all the bits that are previewable before my live class tomorrow. So lunchtime tomorrow. Okay. So thank you very much for coming along today, guys. Really, really appreciate it. Obviously some grumpy people in here today disliking the video, but let's try and overcome that with some likes, shall we? Okay. Always like the videos if you've learned something. Organic chemistry, we are getting to that. I promise we are getting to that. I think we need to spend a bit more time on it because I think a lot of people haven't actually completed all the organic and stuff. So we'll see how we go. All right. So thank you very much, guys, for coming along. Make sure you drop us a like and spread the word, please. Okay. I'm going to, you know, I'd love you guys to just get on social media as well. Get on your Twitter, get on your Insta, do whatever you need to do. Just tell people what you're doing, okay, with us here at Taylor Tutors, and that would be absolutely amazing. So yeah, thank you very much for coming along, guys. We're working hard for you, and just yeah, keep going. And obviously when there's any more news about how exam grades are going to be announced and when and all that stuff about the exams and UCAS, then we'll keep you updated as well. Okay, so thank you so much, guys. Look after yourselves and each other, and I will see you tomorrow at 3 o'clock.